Hello, everyone. I'm Nikhel Gupta, and I'm a postdoc fellow at the MLAI Future Science Platform. It's a platform for machine learning and the domain sciences. And I'm working at the Aerospace and Astronomy department. Today, I'm going to talk about peculiar radio morphologies that we discovered in the ASKAP radio data using an unsupervised machine learning method. All right, to begin with, what is ASKAP? ASKAP is Australian Scale Kilometre Array Pathfinder telescope. It's located in the Murchison region of Western Australia. It's about 800 kilometers north of the Perth city. And the telescope is equipped with 36 dish antennas, and all of these have these phased array feeds, which really help you to look into survey large amount of sky in very less integration time, for what we call the peculiar radio morphologies. So here's a standard cartoon of non-peculiar radio morphologies. So for example, here I'm showing a cartoon where radio emission as a complex radio emission with X as a host galaxy. Then you have other galaxies where you have radio emission in the form of two jets and the host in the center. There can be morphologies where you have two radio lobes far away from the center, and also there is no radio emission in the center. You could have sources where the radio lobes are bent due to some environmental effect, and there is a host here as well as the optical host. These are the bent-tailed galaxies. So the peculiar radio morphologies are those which are, very strange shaped radio morphologies, and we don't really know like exactly how these radio morphologies are formed, or the shape that we see, that how that shape came into being. What's the physics behind that? So these are all the peculiar morphologies that I'm talking about today. To begin with, I'll quickly outline that what I'm talking about. I'll talk about our ASKAP observations that are used to find these peculiar morphologies. I'll talk about the machine learning method very quickly, and then about how we select these peculiar radio morphologies out of such a large data. And I'll show some examples of peculiar sources like circular sources, also known as odd radio circles, and some of other peculiar radio emissions, which are not exactly circular, but they are very peculiar, as you'll see. All right, so ASKAP, Australian Square Kilometre Array Pathfinder. I'm basically using three surveys, which are the pilot survey ones. The Evolutionary Map of the Universe, DINGO, and the other one is the SWAG-X. So three of these. As you can see, all of these are dubbed after the name of animal or bird. There is nothing for SWAG-X, so why not a cat? Well, the EMU survey, it covers around 270 degrees scared of the sky. It's a pilot survey, and the sensitivity is like 25 to 35 microjansky per beam. Very nice beam width, so good resolution. And using algorithm, when you can use the Celebi algorithm in this case to find out the sources in the radio map. There are around 220K, 220,000 radio components in this one, and those which are associated with the complex radio sources, about 41,000 of those. So around 18% of the complex radio components. And in this project, because we are trying to find out the peculiar, complex radio morphologies, which are very strange looking, and we don't know the physics behind them exactly. So I'm just using the complex radio sources. Yeah, for DINGO as well, the sensitivity is very, very fine. There are around 4,000 complex radio components in this one. For SWAG-X, there are 21,000 radio components, and if we look into the gamma 09 field, there are about the sensitivities around 30 to 35 microjansky per beam. So three surveys. Other than that, I'm using publicly available data, like the infrared data or optical data, using legacy surveys, tests, or SDSS, as you'll see in the image here. All right. So, one could say that the total number of sources that I'm looking into is around 41,000 in EMU pilot survey. So, why really we need machine learning? So, just a reminder that the full EMU survey is going to detect more than 40 million radio galaxies. And it's close to impossible for a group of humans to look through all the images and find out, if we want to streamline or finding new sources or discover new things, it's really close to impossible to do that manually. So that's why we need some machine and learning methods, and we're developing some algorithms here. All right, what machine learning method I'm talking about? I'm talking about the self-organizing maps, which is a neural network that provides an very efficient way, to reduce a very high dimensional data into low dimensions to make sense of the data on its own. It's an unsupervised machine learning method. So by unsupervised, I mean that it doesn't need a truth that, well, you give a data and it tries to make sense of the data on its own. All right. And the final one is it's a neural network, which constructs a representative feature map. So by representative feature map, I mean a map which represents the data. And this is done by calculating similarities between neurons in the feature map and the images that we provide to the network. So for example, here here's a SOM lattice. It's a 10 times 10 lattice, and each of these boxes is one neuron. And if you give a random starting to these neurons and then pass these radio images to the network, and because it's an unsupervised method, it makes sense of these images on its own. And in the end, what you get in the end is a representative map, as it shows now after training. So, for example, the images on the top, they are complex sources, probably FR1, FR2 kind of sources. Then there are double lobe sources here. There are sources where lobes are far apart from each other. So all these kind of sources. But well, these are all non-morphologies or more conventional morphologies. So there's nothing new about these. So how do we find these rare and peculiar sources? Well, we don't really use the SOM lattice, but what we can use is a similarity, because, as I said, similarity is calculated between each neuron and the data set, and then that data set goes to one particular neuron, which is called the best matching unit, or BMU. But in case of the rare unusual sources, you can't expect it that all the data is clustered in one neuron. So in order to find out what are these rare sources, one can use the similarity that is calculated between the data and the neuron. So for example, in this plot, I'm showing a histogram of similarities in the form of Euclidean distance. So higher the Euclidean distance, less is the similarity between a neuron and the data set. And you expect to find, at the higher Euclidean distances, you expect to find all the rare and unusual or peculiar sources. So I'm showing here distributions for the EMU, SWAG-X, and DINGO dataset in 3 different colors. And what we do is we took a sample of 0.5% sources, which are highly dissimilar to any of the neuron in that lattice, and which have, of course, a highest Euclidean distance because they are dissimilar. And doing that cut, we get top 0.5% sources, and they are about 200, 120 sources in EMU, SWAG-X, and DINGO surveys. All right, so we then kind of reduced that 65,000 complex components into, like around 320 complex galaxies that we can, one can visualize on it, each of them to find out that if that source is really weird, or what's going on in those sources. And we looked into these 320 sources manually, visually inspected them in different frequencies. And here are some of the examples that I'll show next. First, the circular sources, which are also called the odd radio circles by Norris et al. So these were found when someone looked into these radio maps by eye. And we also independently find these sources, the odd radio circles, using our machine learning method. So here, what I'm showing here is in the left panels is the radio only image, and in the middle is the infrared image, and on top of that there are radio contours, and the third panel is just the zoom in version of the second panel. Also showing the IDs, which means the ID number at which it is inspected, and because it's rated according to the peculiarity. Highest Euclidean distance has ID 0, and the 200th source, which is the 0.5%, because we select the 0.5% or 0.5% sources, and also not the Euclidean distance here. So we do find a couple of forks which were found manually before by Norris et al. 2022, which again shows that our method is working fine. All right, so these orcs are very peculiar. They were well taken by the press as well as the science journals. We find two new orcs now with this unsupervised machine learning method. One orc in the SWAG-X survey, and the other orc in the EMU survey. So this one was actually also found manually, but it was never published. And we independently find it again using our machine learning method. So two new odd radio circles. Can see these odd radio circles, the new ones, in a better way. So here I'm showing optical image in the background and radio contours here. We found around 5 sources A, B, C, D, E here, which are near this OC candidate in the radio emission of this OC candidate. A is probably a star that we found using the parallax and the proper motion measurements from the GS survey. But the other 4, B, C, D, E are definitely galaxies, and probably the redshift of the whole system is around 0.08, as we find a couple of spectroscopic redshifts, I think, of galaxy B and C here. We also looked into other frequencies. For example, in the VLA 3 gigahertz image, it seems like it could be a very strange VAT, if it's a VAT, with very strange turnaround 90-degree angles, and maybe the center is P. But definitely requires further investigation, and we're looking into, put through a Meerkat proposal to look deeper image of this system, and looking into other frequencies as well. All right, and the other one, which is in the EMU survey, so very circular, and we find 4 galaxies near this orc, and for a couple of these, the redshift is around 0.34, and for the other 2 it's around 0.22, but these are all the photometric redshifts, and we couldn't find spectroscopic redshifts in the literature for any of these galaxies. But very interesting circular system, should be investigated further, and we're doing that. We'll be doing that using the Meerkat data. All right, so these are the circular sources, but other than the circular sources, there are other peculiar radio emissions that we found, and I present a few of these here. So these are not exactly circular, but close to circular as well, but very peculiar. So for example, these two in the EMU survey, where on the left you see a very strange near circular emission. And it seems that the source A here is an elliptical galaxy, and it's probably emitting a jet here. Like this, and somehow due to the environment, and it seems to be close to a cluster, so this forms a shape of a garden sprinkler that it's sprinkling in this direction. and or maybe it's rotating. So should do further investigation of this source. Another very peculiar source with the B galaxy, it's a lenticular galaxy here, and a compact source A here in the center. So it seems that the B here, it's emitting a jet in the right direction, and when the jet in the left, it gets mixed up with the radio emission from the compact source A and forms this circular source, circular shape. So very peculiar again. Couple of more in this RAGEX survey. So the one in the left, it looks like an end-on remnant radio galaxy with the elliptical galaxy in the center, but it does shows these circular features on the edge, which are very similar to the odd radio circles. So this one should be investigated further as well. And then finally, another galaxy, another system where we have a compact source a galaxy here, and another galaxy B here. Could be a very strange VAT as well, because it's possible that this is host at A, which is emitting a jet towards the direction of B, and maybe this diffuse emission is a result of the radio emission of both A and B. C is a star that we found from the GEA survey measurements of parallax and proper motion. Right, so I showed you that a machine learning method which can detect, can be used to search for the very peculiar rarest sources in a radio survey, or in fact, it can be used in any survey, any wavelength as well. Just have to train it again, I think, to go to a different wavelength. We selected very few sources, top 0.5%, and find the previously known odd radio circles, as well as we find two new odd radio circles and several other peculiar radio morphologies. So a few of these conventional morphologies, like the FR1, FR2, bent-tail galaxy, resolved star-forming galaxies, or diffuse emission from the galaxy clusters, which I haven't shown here due to the time limit. But soon this paper will be out. It's submitted to a journal and waiting for its waiting for the referee review. Thanks a lot.